In this lesson, we're going to be using residuals to determine how well lines of fit model data. We're going to use technology to find lines of best fit, and we're going to distinguish between correlation and causation. One way to determine how well a line of fit models a data set is to analyze residuals. We're going to talk about that right now. A residual is the difference of the y value of a data point and the corresponding y value found using the line of fit. A residual can be positive, negative, or zero. A scatter plot of the residuals shows how well a model fits a data set. If the model is a good fit, then the absolute values of the residuals are relatively small, and the residual points will be more or less evenly dispersed about the horizontal axis. If the model is not a good fit, then the residual points will form some type of pattern that suggests the data are not linear. Wildly scattered residual points suggest that the data might have no correlation. And if we look at this graph right here, here's our line of fit, and then this is a data point, and then this is a data point. Okay, and to calculate the residual, we just take the difference of this y value and this y value, and since this is above the line, this is a positive residual, and then since this data point is below the line of fit, this is going to be a negative residual. If there was a data point on the line, the residual would be 0. In example 3 in section 4.4, which is the last video lesson that you watched, the equation y equals negative 2x plus 20 models the data in the table shown. Is the model a good fit? Okay, so here we have the table from the last section, which is the weeks and then the sales of the DVDs. And then we have the same exact table right here, but now we want to fill in this category, which is the y value from our model. Okay, so in this case, we have y equals negative 2x plus 1. You can use a calculator for these simple calculations. In this case, we don't even need one. You can just do it in your head. Okay, when x is 1, okay, that's negative 2 times 1, which is negative 2, plus 20, which is going to be 18. I'm going to zoom in a bit on this. And then because if we look at this, the slope of this line is negative 2, I can just go down 2 each time. So this is going to be 18, 16, 14, 12, 10, 8, 6, and 4. Now the residual, remember the residual is the y value from the data set minus the y value from the model. So I just have to do this column minus this column to get the residual. So 19 minus 18 is 1. 15 minus 16 is negative 1. 13 minus 14 is negative 1. 11 minus 12 is negative 1. 10 minus 10 is 0. 8 minus 8 is 0. And then we get 1 and 1. So I'm going to zoom out now. Next thing I'm going to do is I'm going to plot these residuals. Okay, so what that plot's going to represent is the x-axis is going to act as our line, and then their y value for the specific x value is going to be how far that data point is away from the line. Okay, so I'll just plot these really quickly. So 1, 1, and then 2, negative 1, 3, negative 1, 4, negative 1, 5, 0, 6, 0, and then 7, 1, and 8, 1. All right, so we've successfully plotted our residuals down here. And finally, it asks, is the model a good fit? Well, let's look at it. Okay, I would say yes, this is a good fit of the data because we have 3 points which are above the line. We have 3 points that are below the line, aka 3 positive residuals, 3 negative residuals, and then we have 2 points that are right on the line. Okay, so these would be 0 residuals. Okay, and there's no like pattern here that's showing us that this might not be a linear relationship. So overall, I would say that this is a good line of fit for this data. Anyway, now we're done. The table shows the ages X and salaries Y in thousands of dollars of 8 employees at a company. The equation y equals 0.2x plus 38 models the data. Is the model a good fit? All right, so once again, we have our table of values, the age of the person and their salary in thousands of dollars. Okay, and that is rewritten right here. Okay, so now we want to figure out what our model would expect these ages to produce as a salary. So for these calculations, I would recommend using a calculator just to save yourself time. If you really want to do it by hand, that's fine. But for these, you can totally use a calculator. So I'm going to zoom in on our table here. So using the calculator, I get 45, 45.4, 46.2, 46.6, 47, 47.4, 48.6, and 49. Okay? And now what I have to do to figure out my residuals is do the actual value of the data point minus the model y value, and then that will give us our residual. So in this case, I'm going to get -3. Here I get -1.4. Here I get 0.8, then 3.4, then 5, then 3.6, then 0.4, and -4. So next I'm going to plot these residuals on the graph given to us. So 35, -3 will be right here. And the next one will be 37 and -1.4. So that's somewhere right around here. Okay, the next one is going to be 41, 0.8. So 41, 0.8 is somewhere around here. And on these plots, when you're using decimals and you have a small room for accuracy, it's okay if it's not 100% accurate. So now I'm going to go back. I have 43 as an age, and that's 3.4. So that is like right around here. Then 45, which gives us 5. Then 47, which gives us 3.6. Then 53, which our residual is 0.4. Something like that. And then 55, our residual is -4. All right, so now we need to figure out if this model is a good fit. Okay? And I would say no, because we see at the beginning of our residuals, the residuals are below the x-axis, and then as we move on, they go above. It kind of has this pattern right here. And a pattern that, if you ever see a pattern here, it might mean that the data is not linear. Okay? We're trying to fit a linear model, and if the data is not linear, then a linear model won't fit it all too great. Okay? So overall, I would say that this model is not a good fit of this data because it seems like we're going to have something that is not linear. Anyway, now we're done with this one. Finding lines of best fit. Graphing calculators use a method called linear regression to find a precise line of fit called a line of best fit. The line of best fit models a set of data. A calculator often gives a value r called the correlation coefficient. This value tells whether the correlation is positive or negative and how closely the equation models the data. Values of r range from -1 to 1. When r is close to 1 or -1, there's a strong correlation between the variables. As r gets closer to 0, the correlation becomes weaker. Okay? So in this linear regression that we'll be doing, a strong negative correlation is a value close to -1 for r. Something close to 0 means that there's not really any correlation or no correlation. And then something close to +1 means that we have a strong positive correlation. The table shows the durations x in minutes of several eruptions of the geyser Old Faithful and the times y in minutes until the next eruption. Use a graphing calculator to find an equation of the line of best fit. Then plot the data and graph the equation in the same viewing window. Part B. Identify and interpret the correlation coefficient. Part C. Interpret the slope and the y-intercept of the line of best fit. All right, so there's a lot going on here. And we're going to use a graphing calculator. And Desmos is my graphing calculator of choice at the time of recording this video because it's free and you can use it on your computer. Okay? So we're going to go to desmos.com right now. And the way that we can make a scatter plot on Desmos is by hitting this plus button in the top left corner, if you see my mouse right here, and then hit table. Okay, this right here will allow us to input our data. Now, I have the table loaded on my other screen so I can see it, but it might be annoying to go back and forth, but there are ways to figure it out. Anyway, I will start inputting the data. So my x values are 2, 3.7, 4.2, 4.2, 1.9, 3.1, 2.5, 4.4, and 3.9. Okay? And then those corresponding y values are 60, 83, 84, 58, 72, 72, 62, 85, and 85. Okay, now you can't see anything here, and that's because on Desmos, this is our default window, so we need to change our window. You can either scroll out and see the data, but now it's all clumped together. So if you hit Shift and click the axes, you can stretch them out and figure out what the best window is for your data. So I'm going to do something like this. Spread this out a little bit more. So anyway, there is my data. So now that we have our table plotted, we want to use this to find a line of best fit. Now, in Desmos, this is how you do it. We go to a new equation bar in number 2. So I'll click that. And then what I'll do is I will hit Y and then hit the number 1. It automatically goes to Y sub 1. And that is this list right here. Okay. Now, to get a best fit, I'm going to hit Shift and then the button right below Escape, which looks like a little squiggly thing like this. Okay, so if you go to Escape on your keyboard and go below that and hit Shift and that button, this will show up. Okay, and then what we want to do is, for a line, we can use slope-intercept form. So I will do mx, but nothing pops up because I need to say x1. So if I type 1 next to the x, it automatically goes below there. And then I will hit plus b. So instantly you can see that our statistics come up. Okay, so if I zoom in here, we have our m value is 11.99, which is pretty close to 12, and our b value is 35.1068, which we could round up to maybe 35.1 if we go to the nearest tenth. Okay, and then we see our r and our r squared value. Okay, well, r is the correlation coefficient. Okay, this tells us how correlated the data is. Okay, and we see that our number is 0.9787. This is really close to 1, which means this is very strong positive correlation. If r was negative, it would be a negative correlation, but r is positive. And this r squared value is just this value squared. Okay, and what this does is it's a good way to compare how strongly correlated things are, both positive correlations and negative correlations. Anyway, we also see an option to plot our residuals, which we could do. I'll show you what that looks like. So if I hit that, zoom back out, this data right here is just the distance between the line, the y value of the line, and the y value of the data point. I should say the difference between the y value of the data point and the y value of the line. Anyway, so those are the residuals. That's how to do that on Desmos. The original question asked us to graph this line, which we've done. Okay, and it's asked us to identify and interpret the correlation coefficient. Now we've already identified it, which is r, okay, and we kind of already interpreted it too, which means that our data is very strongly correlated, okay? And then for part C, it says interpret the slope and the y-intercept of the line of best fit. So I'm gonna go back to the other screen. M is right around 12, okay, if we round it. And then B was about 35.1, if these are both rounded to the nearest tenth. Okay, so our equation would be y equals 12x plus 35.1. Okay, so now we have written our slope-intercept form equation. Okay, we could use the more precise version, but this is fine for now. Okay, and now we have to interpret it. Remember, interpret means what does this equation mean in the context of the problem? Well, x is the duration of the current eruption, and y is how long it takes till the next one. Okay, So what this 12 means is the time until the next eruption increases by about 12 minutes for each minute that the duration increases. So the longer the current eruption is, you have to wait longer until the next one, okay? Now, the y-intercept is about 35.1, and remember, the y-intercept is the value of y when x equals 0, but it doesn't make sense to have a 0-minute long eruption, so it doesn't really make sense to have any interpretation of the y-intercept. So there is no really interpretation of the y-intercept for this one. Anyway, now we're done with this one. All right, we're going to talk about interpolation and extrapolation right now. Using a graph or its equation to approximate a value between two known values is called interpolation. Okay, so this means that we're estimating something inside of a data set. Okay, using a graph or its equation to predict a value outside of the range of known values is called extrapolation. In general, the farther removed a value is from the known values, the less confidence you have in the accuracy of the prediction. So for this example, we're going to refer back to the previous example. If you remember, our line is y equals 12x plus 35.1, or you could have just done 35 to round, that's fine. Okay, and approximate the duration before a time of 77 minutes. Okay, so if we look back at that previous table, we see that 77 minutes is within the range of data. 85 is the longest, and then 60 is the smallest. So 77 is within that. So this would be an example of interpolation. Okay? So since the time before our next eruption is our y value, we'll plug a 77 in for y and solve for x for part A. So since 77 minutes is the time that we are waiting until the next eruption, that is our y value. So we're going to plug this in for y, and I get 77 equals 12x plus 35.1. I'll subtract 35.1 on both sides. And using my calculator, I get that 77 minus 35.1 is 41.9 is equal to 12x. And now I just have to divide this by 12 on both sides to get my approximate time of the previous eruption. So once again, using my calculator, I get 3.5 minutes rounded to the nearest tenth. So that means for part A, if we go back up here, the previous eruption was 3.5 minutes, or 3 minutes 30 seconds about. So that's part A. Part B, predict the time after an eruption lasting 5 minutes. Okay. Well, I'm going to go back and look at our table. We see that our time durations are in between 1.9 minutes and 4.4 minutes. So 5 would be outside of this data range. So that would be an example of extrapolation. So I'm going to do the same type of thing, but this time this eruption time is the x value, and we want to predict our y value. Okay, so I'll do the equation. Y equals 12 times 5, because that's the number of minutes that the eruption lasted, and then plus 35.1. Okay, well, this is going to be hopefully pretty easy without a calculator. We get 60 plus 35.1, and that gives us 95.1 minutes. You could drop the decimal and just say about 95 minutes until the next one. And now we're done with this one. Now we're going to talk about correlation and causation. When a change in one variable causes a change in another variable, it is called causation. Causation produces a strong correlation between the two variables. The converse is not true. In other words, correlation does not imply causation. Okay? So for example 5, tell whether a correlation is likely in the situation. If so, tell whether there is a causal relationship. Explain your reasoning. So for part A, time spent exercising and the number of calories burned. Well, that would make sense to have correlation there because the more you exercise, the more calories you burn. And the calories being burned is caused by the exercise. So there is correlation and causation here. Slide it over here. And causation. For part B, the number of banks and the population of a city, okay? Well, there might be correlation, okay? Because if there's more banks, that might mean that there are more people that are going to those banks. But I would not necessarily say that there is causation there. So I'm going to write correlation down. But I'm not going to write causation down because I don't think that if you build more banks in a city, that necessarily will increase the population or cause the population to increase. Okay, so this would be an example of correlation without causation. And now we're done with this one.